In these few videos, I will show you how to create a cantilevered structure using different element types. The first element type that we're going to use is the beam element, and that's the one I'm going to show you first. So we'll create a new model. We'll use the standard 3D, static, and structural options. And since our model was defined using parameters, we are going to use those for convenience sake. So I'll start by creating my first parameter A. I'll specify the unit type to be length. I'll specify my custom unit to be millimeters just for convenience sake. And I'll enter my first dimension, which in this case is 100 millimeters. I'll add another parameter B. Although CivilFEM uses B as a reserved local variable, so therefore I'll just change it to B1. I'll enter a value of, let's say, 150. I add another parameter for the length, and let's make that 180. I'll enter parameter M. Let's make that 20. I'll also enter the width parameter as such, as well as the thickness parameter. Now this is quite convenient because then I can use this to do other calculations with as well. Right, so these are the parameters that I need. Let's just reshift this a little bit. And now we're going to start creating our model. So for beam elements, we need line elements or curves. And I'll create the first one to be a length of A, as defined previously. So that provides us with the first curve over there. The second curve will be from A to B1, and then from B1 to L minus M, and then from L minus M to L. So that will be the 4 lines that I need. So there's first curve, second, third, and fourth curve. All right, so next up, after I have this geometry, is to start with the model tab, where I'm going to define a steel. I'll just use the first one and modify the parameters to suit my needs. So I'll just use a different value over here, let's say 195 gigapascals, if that is the steel that you have chosen. And then after using that, we now need to create a model or a beam section, cross section. Now in this case, we don't have a standard steel section with the dimensions that I've used. I can also not use the steel by plates option because this only works when we have 2 or more plates. In this case, we only have a single plate, so that results in a single integration point, which is not solvable. So we cannot use this. And under steel by dimensions, we don't have closed section options either. So I'm left with the generic option only. So for the generic section, I need to specify the area and areas of inertia. So I'll specify the material, which in this case is the steel, and area is simply W times T. So that's quite convenient. That's why I've chosen those parameters, so I don't make a mistake in my conversion from millimeters to square meters. And then for IY, Y, and IZZ, I now need to specify that according to my formula of a 12 width times depth to the third. But now what is important is to realize that these Y and Z axes are local coordinate systems for the elements and does not necessarily coincide with the global coordinate system. So it's really important to know what the local coordinate systems are for these elements. So what I'll do is I'll start by entering these values, but make a note that I have to check afterwards whether I've used them the right way around. So I'll start by saying 12 times W times T to the third for this one, and in this case I'll swap it around. So I'll say 12 times T times W to the third. So what I'm noticing is that my I value around the Z-axis is higher than the value around the Y-axis. So now I need to check after I've created the structural members whether that is indeed the case. And I'll do that. So I'm going to now create my structural members by going to the meshing tab, where I'm going to create beam elements using this generic section that I've just created and selecting the curved geometries. So now I've automatically created 4 structural elements. And this is where I can check what the local coordinate systems are for these. So here I see that X is in the global X direction, but this was purely by accident because X direction for the local beam elements are always in line with the curves, whereas the Y and Z values are then in some other direction. So the Y vector in this case actually coincides with the Z axis of my global system, and the Z axis of these local element coordinates coincides with the global Y negative axis. So this means if my beam is supposed to bend about the global y-axis, that my lowest inertia of area should be about the local z-axis. All right, so that means I have to go back to my general section and check that the z-axis is indeed the lower value. And as I can see over here, indeed, it's exactly the other way around. So I'm going to cut and paste this, enter it as such, cut and paste that, cut and paste that. Right, so now my formulas are the right way around, so that the lowest moment of area value are about the local z-axis, which coincides with the global y-axis. Right, so now my generic section has been properly defined, and I can proceed with the next step, which is to mesh those 4 structural elements. So I'm going to apply a mesh, save the model, overwrite one of my existing models, and we can see down here in the progress bar that meshing is started, and there we see the mesh of these 4 structural elements. Now what you should notice is that the element lengths are not the same, and the reason for that was that the default mesh controls for each structural member was set to a number of elements. So that means there are 10 elements in each section, which isn't required. So for instance, in this last section, we definitely don't need 10 elements, so I can clear that mesh and change this number to 1 because there's no internal nodes required, and I can remesh it. I don't need to remesh each one every time, so I can just continue to the next section, which in this case is model 4, and clear its mesh and modify that to maybe be 1 element as well. And I'm not going to mesh it immediately. I first want to change this parameter as well. So I'm going to clear that mesh and change this parameter to, let's say, 4. And now I can mesh those 2. And I see, there we go. So there's the first beam section. They are just in a random order as the software selected them. If you want to, just for convenience sake, you can rename these sections to make it clearer which is which. So that is actually section 3, and this is actually section 1. That is section 2. and the last one is the tip section 4. Okay, that's just for convenience sake. Right, so now we move on to the loads section, where we will create a load group, a boundary condition group, and a load case. So we'll start with the load group, and we'll only use one group. We can call it structural loads. And as we accept that, we now have the option to create additional loads inside this group. And for this one, I will create a single load, which will be a load on a point. I will apply it to this structural element, and I will apply it at that location. So for that, I activate the option to pick nodes. So I'll pick node 53, and I need to specify the direction, which will be a vector in the minus z direction with a magnitude of, let's say, 100 newtons. So that is the first load that I will have in my load group. And just to check that I've applied it correctly, I can select my load group over here, and what I do see is the end of the arrow sticking out. The rendering is hiding the arrow bit of the arrow, but at least we can see the end. So that shows us that that load was indeed applied. So now we can move on to the boundary condition group, in which we will accept this default group name and move on to create an actual constraint in this group. And for this, I will apply it to the first group over here, which is the beam 1 structural element, and I will pick this location, in other words node 1, and constrain all 6 degrees of freedom. So now I've created a constraint, and by switching on the boundary condition group over here, we can now actually see the arrows, which shows us that the load was, or the boundary condition was indeed correctly created. The last thing that remains is a load case. And for the load case, we purely define a name as well, specify what loads to add. So in this case, I will add gravity as well as my structural loads. And for my boundary conditions, I only have this one group to add. So I can check, yes, I have a gravity load, a structural load, and I have my boundary conditions group. So that finishes my loads and boundary setup, which I can now also visualize over here to check all the loads and boundary conditions active in this load case. Now, if my model was set up correctly, I should now be able to run. And I know that there is one mistake that I have made, and I've made it on purpose because it's a very common mistake that I found very often when assisting my customers. And I want to show you what the error looks like so that you can identify it and know how to rectify the model when this error occurs with you as well. So let's try to solve it and see what happens. So we'll save the model. We can see input is being created for Marc. It started to solve, and indeed an error has occurred. And this is the error that I said happens quite often and you have to look out for. It says error 2004 on Marc solver. The determinant of the stiffness matrix becomes 0 or negative. This condition is usually caused by the existence of rigid body modes. And what that means is that there are parts that are loose in the structure. In other words, parts that can move without any external force acting on them. And why that occurred in this particular structure was because I had these different structural elements defined, but I never defined any connections between them, which means each of these have their own nodes at those center locations, and those nodes are not connected by default. So to rectify this, I will go back to my meshing options. And here indeed we have the option to merge nodes within a specific distance. So I will select the option to merge all nodes, but only those within a distance of 1 millimeter apart from one another. So any two nodes that coexist within this distance of one another will be merged. So I press OK. And now important to check the output section over here to see that something has indeed happened, and I can see yes, there were 3 pairs of nodes that were indeed merged. So the rigid body merge should be solved by now. So let's check. So we run the analysis, save the model, and we see the analysis started and finished and results were obtained. So that's a good sign. So we can maybe just enlarge, maybe close some of these groups. If at any stage you want to close these groups or reopen them, you can do so over here. This is where we have the options to add or close some of these windows. So under the results, we are now going to open the default result case, which is this one over here. And then we don't immediately see any results. We have to define what we want displayed. So in this case, I want the Z component of displacement to be displayed. I press plot and it shows the colors of the displacement. So I can see that I have 0 displacement at the constraint and a maximum displacement at the tip. I can also plot it in a deformed manner, or plotting both deformed and undeformed, as well as plotting a chart on our beam elements. One unfortunate thing about using the generic beam section is that we don't have any element results in here. So it's not possible to know what the stresses are in the structure. And the simple reason for that is that we've never defined any beam dimensions. You will have to derive the stresses using your relationship between bending moment, thickness, and inertia by getting the results from the bending moment about the local z-axis. Remember, the local z-axis of the elements coincides with our y-axis, and look at those values. In this case, we see a maximum of minus 16.19 Newton meters about the constraint. And we have to multiply that by the thickness divided by 2 divided by the inertia, which will give us the maximum stress at the distance half a thickness away. So that is how we will derive the stresses from a simple beam element where we only have a single plate section. For our more complex and available beam sections, this is not required because then the values of stress are automatically calculated for us. But because this generic section doesn't have any dimensions, the software wouldn't know what stress to produce in this case. All right, so that was the procedure to generate results using a beam element. In the next video, we are now going to create a shell element that represents the exact same section. In this video, I am now going to add an identical structure next to this one, but using shell elements instead. So I'm going to reuse these parameters, but this time around, I'm going to create quadrilateral plates using those dimensions. So for the first location, I'm going to use a convenient distance away from the 0, 0 point. So let's say, let's make that 50 millimeters away from the starting point in the y direction, with point 2 being the next step, point A, and again 0.05. And then for our third point, we will use 0.01 again, but this time it would be 0.05 plus W, and we will keep the Z value at 0. And for 0.4, we will change it back to 0, but in this case, the Y value will be 0.005 plus W as well. So you have done this correctly. This should now generate a plate Right, so let's just check that the plate was created correctly. Now, if you don't see the plate, just switch off the nodal picking, which makes the other entities active again. So now we can see there's our beam section that we've created initially, which should have the same length as this one over here. Right, so for the second surface, we can now also use our parameters, which is useful in this case so that we keep our system parametric should any of these values change, so that our locations will update as well. So for point 1, that x value should be A, which is the location of where the second plate should start and end in this location as well. And point 4 would end at 0.05 plus W, as well as point 3. So point 2 should end at point B1, and point 3 should end at point B1 as well, but our our Y value will also be 0.05 plus W. So let's just see if we've done that correctly. So I see I have to just correct the locations of these points on surface 2, and the reason for that was I incorrectly specified those locations. That should be 0.05 for point 1 as well as for point 2. So that is point 1, and for point 2. Okay, so that is our second surface. So there's the first surface, our second surface, and now we just need to complete this for surface 3, and I'll do that by creating another surface. All right, so our third surface will start in the x direction at location B1 and also at 0.05 section 2. That will be at location L minus M, also at 0.05. Point 3 will also be L minus M at 0.05 plus W, and point 3 would be back at point B1 at 0.05 plus W. Let's just check. That seems to be okay. Right, so there's the next one in place. And so I just need one more for the last one. And for this one, we will just use L minus M again, 0.05. That will be L, 0.05, L, 0.05 plus W, and L minus M, 0.05 plus W. Right, so there we have our model, and as I said, this is now all parametric. So if I change any of these values, sorry, not there, not the value, the formula. Right, so the reason this doesn't work is because we already have a mesh. So if we clear the mesh and change this, we can now see that value has changed, but some of the other values did not change. So that means we made a mistake at one of the locations. Okay, surface 2 is correctly defined, surface 1 wasn't correctly defined. So I need to correct that location, and that would be point 3. 1, 2, 3. So point 3 was supposed to be at point A. Right, so there we have fixed that. So let's see if I now change any of these dimensions. Right, so that seems to be working correctly. Okay, so now we can see our structure updates parametrically. If I change the width value, that changes. And if I change these values back, we see indeed all those values adapt accordingly. So we can make that 120, maybe make that 80. Okay, so now we have a nice parametric model for both the curves as well as the surfaces. The next step after we've created the geometry is to move on. Now in this case, we have shell elements that only has a thickness, and we have already defined our steel material, and we don't need to define any cross sections for shells, so we can move on. And under meshing, we are now going to define a new shell property, which is purely going to be a thickness of T, and we're going to assign this to our 4 surfaces. So over here, I'm going to select these 4 surfaces and assign that to my shell structure. So there we see we have 4 structural elements for shells, and we're going to mesh them to see what their meshes look like. And I see, okay, I have chosen the wrong element type. I don't want triangular elements, I want quadrilateral elements, so I need to correct that. So for this, I'm just going to go to mesh control, and under parameters switch to quadratic. The element sizes are way too large for a model this size, so I will change that. Let me have the elements at such a size that there are at least 4 throughout the width. And the reason I want an equal number is so that I have a node in the middle over here where I can apply my load. So I'll make the element size width divided by 4, and that should be enough. So I can just use that equation in all of these. Just make sure that you change all of them back to quadrilateral elements. The third one as well. Quadrilateral element, H size, W over 4, and for the last one as well. Alright, so let's remesh and see what this new mesh looks like. Oh, I see I haven't selected the others. That's a mistake. So let's just remesh them as well. Alright, and there we see our meshes. We see the visualization of the thickness, even though the thickness is only a property. So just as before, these various shell structural elements won't be connected by default, so we have to merge their nodes. My beam elements meshes have been removed, so I just need to remesh them as well. And what I can see now is that my load didn't move along with my parameters. So that is a problem. I just need to look into that quickly. So let's go to the load group. If I go to my structural loads and I see this is where my load was placed, I can indeed see that the load wasn't applied at a formula location, it was placed at an actual location. So I'll again modify this to be L minus M instead of a constant value. So that is important to rectify. Okay, so since I've already have this group, I can just add another single load. And in this case, I'm going to use shell 3 as the structural element on which to apply the load. And I'm going to apply it again at a node. So in this case, I'll use the node over there. And then instead of keeping this value like this, I will just again make this parametric instead, which in this case would be 0.05 plus W over 2, so that I keep it at that location also parametric. And then for our constraints, the constraints are going to be a little different, because now we need to first activate the constraints and add a linear constraint. Now, a linear constraint I can apply on this shell structural element over here, and that allows me to select a curve. Now, in this case, I don't want to apply to all 4 of those curves. So to deselect those lines, so that's the only line where I'll be applying it, and I'll constrain all my degrees of freedom on that one as well. Right, so that gives me boundary conditions for that. The only thing that is left to check is what's going on over here, because I don't see that applied load. So let's just see what have I possibly done wrong over here, because this load is supposed to be applied at that location over there. And let's just see why. Oh, that's right, I haven't specified the magnitude correctly, as well as the direction. So the direction should also be 0 in the x direction, but -1 in the z direction. Right, so now I see both my boundary conditions and loads applied, and that should be sufficient, except that we still need to merge all the nodes in the model within a distance of 1 millimeter. And we can see quite a number of nodes have indeed been merged, so that's a good thing. And now we can solve our model by first saving it. Results have been obtained, so let's have a look. Open the default file again, and let's look at the Z displacement. I'll just magnify the deformation, and there we can see our values. All right, so that was very useful. If we now need to pick results at specific locations, what we can do is to use the list option, where we specify that we want to select elements or structural elements. So now I have selected both the beam and the shell, and by doing that I get access to my results. And I can see meter units doesn't give me enough digits, so I'll rather change the environment to provide me with custom units, where I can change the principal unit of length to millimeters. And then when I go back to my results and my list selection and reselect those 2 entities, I get the results in millimeters. So yeah, I can see the various nodes and their displacement values. With regards to the element results of the shell elements, we can plot the von Mises equivalent stresses as well. We obviously don't see any values for the beam elements, but we can see that very nicely for the shell elements, and we can see the through thickness stress changes as well for these shell elements that are actually only flat elements like this, but through a thickness property actually provides us with an additional dimension on these elements. All right, so that concludes the second session where we created the beam represented by shell elements. We will now continue and create two additional representations of the same beam, but using solid elements. In this case, I could generate the solids using my primitives option, where I would need to recreate those solids using my parameters, or I could use the extrude option where I simply provide it with those original shell elements. So it would be better if I simply copy and translate the already existing shells or surfaces and use them in conjunction with the extrude option. So the easiest method is going to be to copy these existing surfaces by using the translate option and then extruding them. So I'm going to use this option where I copy them, and I'm not going to make them independent. I want to retain them to keep them referenced to the original geometry, and I'm just simply going to specify a new distance of 0.05 millimeters in the y direction. So there we see our copied geometry, and to check that they're still parametric, let's just change one of these values. So let's just remove the mesh of all the elements and then change this value, and yes, indeed we can see our model is still parametric. And we're going to do the same for the copies of the copies. I'm going to translate them again using a vector, and again move them in the y direction of 0.05 millimeters, and there we go. So they are also copied and linked to the original geometry like this. Right, so we're going to keep those our beam elements. These are going to be shell elements, but these we now need to extrude into the third direction so that we can specify solid properties for them. We need to create a line first, and I'm simply going to do that using a line at the origin, t times 5, just to get it visual. Right, so there we have a line. So now we're going to use this new line to extrude our surfaces into the direction of this curve by selecting all these surfaces. What we see now is that curve was actually used to define the thickness. We didn't need to define a thickness, so that's obviously not the correct way. So we can simply change that by changing 0.2 to be the thickness. Right, so we've reserved these curves for beam elements, these for shell elements. Now we're going to create tetrahedral elements and hexahedral elements in those solids. So we proceed to meshing, and we have the option to create our various solids. So for the first selection, I'm going to select all the extrusions like that. We're going to accept it. And now we simply need to modify the element properties. So in this case, it's a tetrahedral mesh, and the element sizes will be 1 meter, which is far too big. So let's just see what other options we have here. So I'm going to create elements, the thickness of the plate, and we'll just do that for all 4 of those blocks. And to see what those meshes will look like, we can mesh them. Now just remember we need some nodes here right in the middle, so it might be a good idea to just check that we have a node in the middle, and we happen to have one right there, so that is sufficient for us to apply our loads. Right, so let's move on to the last section, where we're simply going to mesh those bodies, but this time with hexahedral elements. So I'm going to create another solid, this time selecting those 4 and accepting that. I now also just need to change the mesh control. So in this case, we're going to use a extrusion mesh, again with an element size of T, where the surface type would be a quadrilateral with edges the size of width divided by 4, so that we have the same size mesh as for the shells. Everything is meshed. Now we just need to apply the additional boundary conditions as well. So I'm again simply going to modify the existing load groups. So if I activate my structural load, I'm going to apply an additional single load at various locations. So in this case, I am going to act the load on that location there and pick a node over there as the point of application. Again, I need to specify the correct magnitude and direction. I'll specify my value, and to keep the location parametric, I will change this value to L minus M, as well as change this value 1.5 plus W over 2 to include that. And there we have that value. So now we can apply the next one on that model over there. Use that node as a guide to the location, which we can then again edit so that it stays parametric. That is incorrect, and the reason for that is I forgot to change the value, the magnitude, and the direction. So let's just correct that. Change the value over there. Now we see the arrow, but the location is incorrect, so that means I've made a mistake over here because I applied the wrong formula. Okay, so that changes our loads. Right, so now the only thing left to do is to correct the boundary conditions as well. So we need to add boundary conditions in this area. So going to the boundary conditions, we are going to add, in this case, surface groups, and I'm going to select this solid and select that face and constrain those 3 degrees of freedom. And I'm going to do the same for this body over there by selecting that face and also constrain those 3 degrees of freedom. So there we now see the constraints. So if everything was set up correctly, we should now be able to solve our model, but just remember to merge nodes in case we haven't done that. And we can see indeed there's a number of nodes that still had to be equivalent. So now we're going to solve the model. And the results have been obtained. So we can load our file, set up the values that we are interested in, and plot our model there. Now what I can immediately see is that something went wrong with the definition of those two solid element bodies, because they are supposed to deflect more or less the same as the other two. So I'll have to interrogate the definition of the solids that I've defined for them. And indeed what I see over here is that we've set up the element type to be linear, which is quite a bad formulation for these tetrahedral elements. So for the tetrahedral elements, which are these guys, let's just change that. So for these elements, we should mesh them with quadratic elements instead, so that it create mid-side nodes for the tetrahedral elements. Now, unfortunately, we've exceeded the number of nodes for the student version, so we will have to change a few parameters. So when we get the message that we've exceeded the maximum size of the licensed product, we can actually select these sections that have already been meshed to check how many nodes and elements was created. So we can see already 1,600. And if we find, where's that solid? There we go. Just reorder them so they're better like that. We can see 3,100. Okay, so this mesh is too refined when we mesh using quadratic elements for the number of nodes that we are allowed. So let's clear the mesh and use a coarser definition. So let's see what can we do. If we change the edge sizes of the tetrahedrons to be t times 2, that will change the mesh density quite dramatically. So I'm just going to change that for the others as well. And hopefully we can get within the limitation of what the software allows us. Right, so let's see if we mesh these ones with quadratic elements. So I'm going to mesh them separately first without meshing the other structures, just to see if we can at least get this number below 5,000. All right, so that seemed quite possible. So just to check that we indeed have quadratic elements, I'm going to switch on the node labels. So yes, there we can see the in-between labels for the additional nodes, so they are definitely quadratic elements. And to see how many elements this created and nodes, so it seems that should be fine. I don't want to mesh the hexahedrals with quadratic elements. I want to mesh them with linear elements, but there's a different property that I have to set to ensure their quality, and that is under configurations. So I'm going to choose the improve bending option over here and mesh those remaining solids with linear elements. See if I can still get in underneath the limitation, and that seems to be fine. So I'm just going to remesh the rest of the structure as well, keeping the mesh on linear elements. So now we have quadratic elements for the tetrahedrals, but linear elements for the hexagons, as well as the shells and beams, with the only exception that under the solution settings, I've switched on improve bending, which will improve the bending for those elements. It won't have an effect on any of the others. So my model seems to be fine. Okay, I forgot to merge those in between nodes. So let's just remember to do that. 1 millimeter should be okay. A lot of merging has happened, so let's just run that again. All right, so there we have results available. So let's open the result file, and I'm going to plot the Z displacements in this format. And there we go. Now we see much better results because we have switched on improved bending for the linear hexagon elements, and over here we've used quadratic tetrahedral elements, which are the best element formulations to use for those. So that concludes this video on how to create the 4 cantilevered beams using different element types.